Anyway, today is about thermodynamics. And before I begin that, I just want to remind you that it's very related to thermochemistry. And thermochemistry is about it's about how energy is transferred. And let me just remind you about that topic here. You should look at the lecture notes and review some of the thermochemistry topics. And let me just share that slide with you and just highlight that aspect of thermochemistry. So thermochemistry really is about understanding endothermic and exothermic, in which we talked a lot about in kinetics. You know that endothermic reactions are reactions in which energy is required to get that reaction to progress. Exothermic reactions are reactions in which energy is released. And so here you see uh, the discussion in chapter 18 on thermochemistry. It talks about energy. It talks about potential and kinetic energy. It talks about state functions. State functions are functions in which the path is independent of the quantity that you get, whereas non-state functions are path dependent. For example, traveling from here to San Francisco, that's not a state function, because if I take it via the freeway, the path is going to depend on how long it takes me to get there, or the distance I travel, versus if you just take a map and measure the distance between San Diego and, say, San Francisco, that's independent of time, of course, and the path that you take, because it's an absolute function. So state functions are independent of path, and that's what you will see in thermodynamics, is that the values of the thermodynamic properties are just based on the final and the initial. Okay, if you measure those, or you get those quantities and you just take that difference, then you have the value for that particular state function. Enthalpy is a state function. Work is not a state function, and we'll see that as well. We also talk about enthalpy. Enthalpy is really the energy of a system at constant pressure. And the reason why we want to state constant pressure is because when we carry out a reaction, we usually carry out a reaction in an open vessel. And so you might say to yourself, well, if it's an open vessel, then really the pressure is not constant. But it is constant, because the reaction is based on the ambient pressure, the atmospheric pressure that is impeding on that particular reaction. Whereas if you close the reaction and it's a closed vessel, if it generates heat, then the pressure will increase, because there's nowhere for that pressure to get released. Okay, so enthalpy is nothing more the energy of the system at constant pressure. And we denote enthalpy by the letter H, and it's a state function. So you can calculate, or you had calculate enthalpy in general chemistry. Okay, the most important part of thermochemistry is understanding how our universe is described. Our universe is everything in which we are talking about. If it's a reaction, if it's a calorimetry experiment, and there's only two participants in our universe: the system that we are studying, and the surroundings. Okay, together that makes the universe. And it's important that you understand that. And it seems like it's easy to understand, but you need to understand that, because when one giveth, the other one takes, because there's only two components in the universe. Okay, so keep that in mind as we go through thermodynamics. No, this is not part of the midterm. Okay, everything's, if you look at the announcement, I tell you exactly what's on the midterm. Anyway, I talk about a system, and I tell you what the process is, whether it's endothermic or exothermic. A classic example is the heating of water as it goes from ice to liquid to gas and vice versa. So we're going to be talking about that process in more detail in thermodynamics. Again, it's about understanding the system and the surroundings so that you guys can define the whether the energy that is involved or the state function that is involved is positive or negative. That's the key in understanding the universe, whether the sign is positive or negative. So the rest of this really is just about talking about heat exchange and making sure that you understand the nomenclature. And if you want, you can read those notes or review it. But I really want to get into chapter 18. And I hope to get through enthalpy and entropy today. And then next Monday, we'll talk about Gibbs free energy and then hopefully finish up this particular section. Really, the crux of thermodynamics is understanding free energy. So we'll be talking about that probably sometime next week. But you need the fundamentals. You need to understand how enthalpy and entropy contributes to the free energy in our universe. The reason why we study thermodynamics is because it really answers. Remember in the beginning of the semester, I told you that really second semester general chemistry is about making sure you understand chemical process, chemical reactions, that we talk about how fast that process takes place. That's the realm of kinetics. We talk about how efficient that process is. That is equilibrium. The equilibrium tells you the efficiency by which that reaction takes place. And then we ask the question, will that reaction actually take place? And that's the realm of thermodynamics. Okay, thermodynamics tells you whether that reaction is spontaneous or not spontaneous. If it is spontaneous, how much energy can you produce from that process? If it's not spontaneous, can you make it spontaneous? Can you make it go if you put in some energy, okay, to make that reaction go? If it's not spontaneous, does any amount of energy make that reaction go? So that's what we are going to be talking about in this particular chapter. I really like thermodynamics because it encompasses all types of science. You need to understand thermodynamics if you're an engineer. If you're in physics, you cover thermodynamics. If you are in biology, you look at thermodynamics as well. So thermodynamics really is a universal science that governs whether a process will take place or not. And so let's take a look at this right here. A spontaneous process, whether it's a chemical or physical change, has to do with whether or not it's going to be spontaneous. For example, if you take water at room temperature and you try and see whether it will freeze, it's not going to freeze. So that's not a spontaneous process. Room temperature, 1 atmosphere. If you take that same water, okay, and you change the condition, lower the temperature, for example, then it will freeze. Or maybe you reduce the pressure, then it can freeze as well. So depending on the conditions that you impose, you can change a process from spontaneous to non-spontaneous. What we're really looking at is if it is spontaneous, is it going to be spontaneous all the way through? Sometimes you might need to give it a little kick to get it going, like starting a match or lighting a match. Once that thing goes, it goes. You don't stop it, but you do need to give it a little bit of push, like a little bit of spark. Okay, so that's what we are talking about here. If it's not spontaneous, like I said, can we make it spontaneous? So when we look at the process of, let's see what's happening here. Thermodynamics, we're looking at the energy of the universe or the spontaneity of a system. But going back to thermochemistry, remember that the energy of the universe is based on two quantities, the heat and the work. And it's defined by delta E equals Q, which represents heat, plus W, which represents work. Okay. Remember the first law of thermodynamics. First law of thermodynamics states that energy can neither be created or destroyed. It's only converted from one form um, to another. You can take, for example, mechanical energy and get heat energy from that. You can take solar energy and get electricity from that. So you're converting it. But the total energy in is equal to the total energy out. Energy is conserved. You can't create it or destroy it. Of course, we need to put an asterisk on that because ever since Einstein gave us E equals mc squared, we can't convert matter into energy and energy back into matter. So you got to put a caveat to that particular statement. But basically, this is the first law of thermodynamics, that the energy of the universe is constant and it equals to the energy of the system plus the energy of the surroundings. Remember that our universe is equal to the system and the surroundings, and that's constant. The heat of the system is equal to negative the heat of the surroundings in this particular statement. And the work of the system is equal to minus the work of the surroundings. Okay, we represent those things that are attributed to the system as a subscript SYS, and those things attributed to the surrounding as a subscript SURR, surroundings. So a modern statement, again, like I said, needs to consider Einstein's equation. So when we have a reaction and we look at the reactant going to product, and there is
Professor,
yes,
you're jumping right through these. Does anybody else need to watch the last slide, or am I the only one?
this right here.
I do.
Okay.
Okay, I guess I should monitor my monitor because I guess there's the delay in terms of this, but this is basically what I was just talking about. Okay, so let's move on to this. If you take a look at a reaction, and you guys covered this in general chemistry, and to extent chemistry 152 as well. We know it's endothermic or exothermic, and we represent that as delta H of the reaction. We cover that in kinetics as well. The nomenclature of enthalpy. And like I said, you guys have been able to do these types of questions where you look up the energy or the enthalpy of the product and the enthalpy of the reactant, and then calculate the total enthalpy of the reaction. Sometimes we call it the heat of the reaction, but it's really the enthalpy of the reaction because we're carrying it out at constant pressure. Okay, constant pressure. Now, the other thing that you should remember is that sometimes we give the delta H value here an indicator of what specifically what that enthalpy is measuring. If we say delta H reaction, so it's sort of generic. It's whatever reaction you have that you're studying. But if we say delta H of combustion, then the reaction itself is a combustion reaction. Or maybe we can say delta H formation, and formation means that you're forming a chemical from its elemental parts, the way the elements are found in nature. So when you take elements found in nature and you produce a product, that's a delta H of formation. And the reason why that's important is because what you find out is that when we have the enthalpy of its elemental parts as found in nature, then we give that an enthalpy of 0 because we need a reference point. Okay, that'll become more clear when we talk about this. Delta H of fusion, remember fusion is the solid liquid process. If I have delta H of evaporation or vaporization, that's the liquid gas process. So again, these things are just giving you information about the process that's taking place, but it's still calculated the same way. You look at the enthalpy of the product and the enthalpy of the reactant, and you figure out the difference based on how many you have. How many means how many moles of that chemical. So if you know the enthalpy of the product, you need to multiply that by the number of moles to give you the total. So you guys are used to that. Um, and it's just a matter of exercising that technique in thermodynamics. Now, the important thing that you need to remember is that we give these chemicals a value. We say that, yeah, the enthalpy of carbon dioxide is such and such kilojoules. The enthalpy of sodium chloride is such and such kilojoules. But the question is, how did we measure that? How did we determine that? Well, we determined that by actually carrying out the experiment. But we need a starting point. We need a reference point. Just like we have a reference point for the elevation of mountains or the elevations of how high we are if we're in, say, a plane. Well, so do we need a reference point for some thermodynamic parameters, okay? And that's what we're doing here. In terms of um, enthalpy, we need to find a baseline. And that baseline is going to be defined for us, the conditions, and then we're going to give it a value. Like I said, just like we determine the elevation based on sea level, we can do the same thing with thermodynamic parameters. Temperature has an absolute scale because absolute zero or 0 Kelvin is a 0 point. We can't go past that. That's the baseline for all temperature. Of course, we don't measure things in Kelvin always. We are used to Fahrenheit if we're here in the US, or Celsius if we're anywhere in the universe. But 0 degrees is based on the freezing point of water. So that's again a reference. Anything hotter than that um, will be above 0 degrees. Room temperature is about what, 17 degrees Celsius, okay, or 72 degrees Fahrenheit. You got to remember that in the temperature scale, 0 degrees Celsius and 0 degrees Fahrenheit are not the same. When they defined 0 degrees Fahrenheit, they actually wanted to figure out at the lowest temperature at what in which water freezes. And so what they did was add salt, and then they tried to freeze it, and then they measured that temperature. And it's actually below 0 degrees Celsius. But anyway, that's a story that hopefully you guys learn in general chemistry. So there's two types of scale that you guys should know. One is a reference and one's an absolute. A reference might be the elevation, an absolute might be in Kelvin. Your age is an absolute, okay? The day you were born is when you start running the clock on how old you are. So the question is, how do we measure the energy of um, systems? What can we do to define a, say, a scale for that? And what we can do is we can um, look at something, and if it's not moving, maybe give that, or it has zero energy, maybe give that zero energy. So take into consideration maybe a car, and the car is not moving, the engine's off and everything. So is that zero energy? And if we look at it and maybe we release the brake, it starts rolling down the hill. Where did that energy come from? Well, it came from the fact that it's elevated. So a potential energy was converted to kinetic energy. Okay. Now at the bottom of that hill, can we say that the energy of the car is zero? And we really can't, because you guys know that the Earth is constantly rotating. And if the Earth is constantly rotating, then this car is also rotating. So the energy is not zero, even though with our reference, it is zero, but its absolute energy is not. And then if you look at the atoms that make it up, these atoms are constantly moving and vibrating because the temperature is above 0 Kelvin. So we need to define exactly what is zero, and that's where standard state comes in. Okay, standard state gives you information about how to define a zero or a reference. And you guys will have to know this because you need to get a reference point for all of this. So because all matter will have energy via vibration or the electrons moving, we need to define a condition by which we can say it's zero relative to everything else. Okay, it's relative to everything else. And so what we have done is define this reference called standard state conditions. And it's the conditions in which we have 1 atmosphere and 25 degrees Celsius. That's standard state. So if we have a chemical found in nature, in its natural process, at 1 atmosphere, 25 degrees, then we give that enthalpy value 0. We say it has 0 enthalpy. And if we heat it up, then it gains energy, then we can measure that enthalpy. It's going to be above that. If we cool it down, then we measure that energy again, and it's going to be below that. But you got to remember standard state because that really is important. And we define our reference based on this standard state. In general chemistry, standard state was 0 degrees Celsius, STP. Remember STP, standard temperature pressure? 1 atmosphere, 0 degrees Celsius. In Chem 201, it's not 0, it's 25 degrees. 298 Kelvin, not 273. So other conditions that define standard state, if you have a liquid or a solid, it's got to be in its pure state. You can't have water as a standard state. Why? Because water is not in its pure state. For example, it's not elemental, so we can't make, it can't be a 0 enthalpy because it's made out of hydrogen and oxygen. Gas has to be at 1 atmosphere, solution has to be 1 molar. So let's take a look at how we denote standard state. We use a super zero. A super zero. Super zero is a superscript 0 or circle. Okay, so all of this right here indicates standard state conditions. So let's consider this right here. We have carbon graphite, not carbon diamond, because graphite is the common form of carbon in the universe. Oxygen gas goes to carbon dioxide. What is the delta H formation? Well, to calculate that, we need to find the carbon dioxide enthalpy, and then because these are found in nature in its natural form, and we have 1 atmosphere, 25 degrees, we assign it 0 enthalpy. So what, for this reaction, which is a formation reaction, what is the enthalpy of this reaction? It's products minus reactant. This reaction is a 1:1:1 ratio. So the product is minus 393.5 kilojoules minus reactant, which is 0. So this reaction has a formation energy of minus 393.5 kilojoules. And that's how we determine the enthalpy of carbon dioxide as well in its gas state. If it was a liquid state or a solid state, then that would be a different number. You have to pay attention to the chemical formula and you have to pay attention to its phase. That's critical. Okay. So you can do that for the rest of these. For the rest of these, again, it's just a matter of finding what these values are and then calculating products minus reactant. Again, it's very important to pay attention to the formula and the phase of that particular species. Here, we see that the delta H for these chemicals are not equal to 0. Why are they not equal to 0? Because, or they are equal to 0, sorry. Because bromine is not found as a solid or a gas at room temperature. It's found as a liquid. So it's a defined 0. We already talked about oxygen, carbon, graphite, sodium, solid. But for this, it's not 0. It's going to be some value. Why? Because water is not in its pure, it's not its elemental state. Okay. Oxygen is a liquid in this second example, so it's not 0. Carbon diamond is not in its most abundant state. And then sodium chloride, again, is a chemical, so it's not 0. You would actually have to find a value for this in the appendix. So that